Welcome to Study Loop.
So in this problem, we are given a reaction equation for the decomposition of sulfur trioxide, which decomposes to sulfur dioxide and oxygen. And the data we are given here are the mass or the initial mass of the sulfur trioxide, which is reacting, and the mass is 0.831 gram. We are given the volume of the reaction vessel as 1 liter. We are given the temperature as 1100 Kelvin, and we are given the total pressure at the equilibrium is 1.3 atm. It's not liter, it will be 1.30 atm atmospheric pressure. We have to find out the value of kp and kc. So first we'll find out the value of kp, and from there we can find out the value of kc. And to find out the value of kp, what we need to know, so we can write down the reaction equation here, which is, so the reaction equation is 2SO3 will decompose to give us 2SO2 plus O2. So if we write down the equilibrium constant in terms of pressure, the expression will be the product partial pressures on top, so it will be PSO2, and since we have 2 of the sulfur dioxide, it will be squared, and times it will be PO2, and in the denominator we will have PSO3. Since we have 2SO3, it will be again squared by 2. Now what we have to do from here is, so we need to know the partial pressure of each of the components at equilibrium. So for that, what we have to do, we are given the mass of the sulfur trioxide, initial mass. From this we can find the initial pressure of sulfur trioxide, and from there, setting up an ice table, we can find the equilibrium pressure of each of the components present. So for that, what we'll do is we'll write down the ideal gas equation, which is PV equal to nRT, where P is the pressure, V is the volume, N is the number of moles, R is the universal gas constant, and T is the temperature. So if we write this for the initial pressure of sulfur trioxide, we can write this as N over V times RT. So we know the value of R, we know the value of T, we know the value of V, we need the value of N. So we are given the mass of sulfur trioxide. From here we can find out the number of moles of sulfur trioxide, which will be mass of sulfur trioxide over its number of moles. The mass is 0.831 gram over the molar mass of sulfur trioxide, which is 80.06 gram per mole. So this will give us a value of 0.0104 mole. This is the number of mole of sulfur trioxide. Now if we plug in this value here and all the other values, it will be 0.0104 mole over the volume, which is 1 liter, times the universal gas constant in liter atm unit, it will be 0.0821 liter atm per mole per Kelvin, times the temperature, which is 1100 K, and from here we will get the initial pressure of sulfur trioxide as 0.937 Kelvin. So this is the initial pressure of sulfur trioxide. Now now from the balanced equation we can set up an ice table for this reaction. So the ice table will be like this, where we have our SO3 as the reactant, then we have SO2, and we have O2. So the initial pressure for SO3, which we have just calculated as 0.937 atm, for SO2 and O2, since they're products, the initial pressure will be 0. Then if we consider the change as x, then the change will be 2x for the reactant, so it will be minus 2x, and for sulfur dioxide it will be plus 2x, and for oxygen it will be plus x, since there is only one oxygen molecule. And then at the equilibrium we will have 0.937 minus 2x as the equilibrium pressure of sulfur trioxide, and for sulfur dioxide it will be 2x, and for oxygen it will be x. That's how it will be the equilibrium pressure for each of the components here. Now we know the total pressure at the equilibrium, which is given as this. And as we know that at equilibrium, total pressure is the sum of all the pressures or all the partial pressures exerted by each component present. That means P total at equilibrium will be PSO3 plus um, PSO2 plus PO2 at equilibrium, and this value is given as 1.300 atm. We have calculated each of the equilibrium pressure. For PSO3 it is 0.937 minus 2x, then for SO2 it is 2x, and for O2 it is x. So if we just we can cut this 2x here, so the value of x will be this minus this, and from here we can find the value of x as 0.363. This is also atm, so the value will be 0.363 atm. Now so from here we can now calculate the equilibrium pressure of each of these, just applying the value of x. So the partial pressure of SO3 will be 0.937 minus 2x, or 2 times 0.363 atm. It will give us a value of 0.211 atm. Similarly, we can calculate the PSO2 will be 2 times 363, which will be 0.726 atm, and PO2 will be just the value of x, which is 0.363 atm. So these are our partial pressure of each of the component at the equilibrium. Now we just have to plug in these values in this expression here. We know value of each of these, so we can just write down or find out the equilibrium constant in terms of pressure. For this, it will be the PSO2 square. So the value of PSO2 is we have calculated PSO2 as 0.726, so it will be 0.726 square times the PO2, which is 0.363, and then in the denominator we will have the partial pressure of sulfur trioxide at equilibrium, which is 0.211, and we have a square over it, and the value which we will get from here is 4.297. So this is the value of Kp for the reaction given. Now from here we have to find out the value of Kc, and we know that there is a relation between Kp and Kc. So Kc is equal to, or Kp is equal to Kc RT all over del N. That means Kc will be Kp over RT whole bracket del N. And from here, we have already calculated the value of Kp as 4.297 over the value of R is 0.0821. We are not writing the units, but while in exam you should write all the units, which we have already shown earlier, and then it will be 100,000 1100k over the value of del N. So the value of del N is basically the difference of the number of molecules of the products and reactants. So for products we have 2 plus 1, total 3 molecules in products, minus the products of reactants, or the molecules of reactants is 2. So the del N will be 3 minus 2, or 1. So the value of del N is 1. And from here we'll get a value of 0.0476. So this is the value of Kc for this reaction.